Hello and welcome to WinXAS Tutorials. While previous tutorials were all about data reduction and raw data treatment, this is the first tutorial about XAFS data analysis. We want to start with the XANES region and introduce procedures to extract coordination geometry and average valence information. As always, the WinXAS software and the XAS data I will be using in the hands-on session can be obtained from the WinXAS website. The analysis of the near edge or XANES region normally uses the calibrated, background corrected, and normalized absorption spectra. For XANES analysis, those data reduction procedures need to be performed as careful as possible to obtain reliable average valence, geometry, or quantitative phase analysis. That structural information comes from a comparison with suitable reference materials possessing known valences and geometric structures. Theoretical XANES calculation is not within the scope of these tutorials. XANES data analysis includes procedures like calculating derivatives, refining a sum of a step and profile functions to the spectrum, and principal component analysis. This tutorial covers the former, while the latter will be the subject of another tutorial. The coordination geometry of the first shell can sometimes be deduced from characteristic pre-edge features. Shown here are the XANES spectra of molybdenum trioxide and molybdenum dioxide. The pre-edge peak in the spectrum of molybdenum trioxide is indicative of the distorted coordination of molybdenum by 6 oxygen atoms, while the absence of a pre-edge peak in molybdenum dioxide corresponds to a more regular octahedral coordination. In a refinement procedure, the pre-edge peak can, for instance, be modeled by a suitable profile function, while the edge position is obtained from the position of a step function. Subsequently, the average valence can be obtained from said energy position by comparing it to that of suitable reference compounds with known average valences. In a best case scenario, a corresponding calibration curve can be obtained to convert the edge position of the spectrum of an unknown material to average valence over an extended range and with a high accuracy. However, the best feature for calibration is not necessarily the first inflection point or the position of a step function, but needs to be determined experimentally by using various procedures. The effect of two different procedures is shown here for vanadium oxides. At the vanadium K edge, the XANES spectra of various vanadium oxides exhibit a characteristic pre-edge peak where the peak height scales with the average valence. Pre-edge peak height can, for instance, be determined either from a profile refinement or a simple maximum search algorithm. While both procedures yield an increasing peak height with average valence, the profile fitting appears to result in a more suitable calibration curve. WinXAS contains a variety of numerical procedures that can be used for data analysis of not only XAS spectra. I will use this tutorial to briefly mention some of them, for instance, selecting and refining the sum of various profile functions to the original experimental data or to first or second derivatives. Coming next is the hands-on session. Objectives will be performing refinements of step functions and profile functions to experimental XANES spectra. Those refinements can be performed to the background corrected and normalized spectra, as well as the first or second derivatives. The vanadium oxide XANES spectra used are included in the tutorials data folder, which can be obtained from the WinXAS website. Let's get started and open the experimental spectrum of vanadium pentoxide. And let's assume we are interested in this pre-edge peak, in the height of the pre-edge peak, for instance, also in the width, the area under this pre-edge peak. This is what we want to extract from this XANES spectrum. Now, we start with selecting a region that only includes this pre-edge peak, and that we can use for further analysis now. So the easiest approach now to analyzing this peak is just to search for the maximum in this trace and take the photon energy or the height for this pre-edge peak and use this for further analysis, for instance, for calibration, comparison with unknown samples to determine their average valence. In the numeric menu, you will find a number of common numerical algorithms that can be used for XAFs or XANES analysis, but of course can also be used for any other type of data analysis. And those procedures include smoothing, for instance, using different algorithms, integration, differentiation, interpolation, Fourier transformation, linear regression, and search min-max, which we actually want to use now. All those procedures are explained in detail in the manual if you are interested in more detail, and they are also referenced there with respect to the literature. So search min-max is what we want to do now. We only are interested in the highest value in this region, which would correspond to the height of the pre-edge. We do want the maxima only, and we do not want to apply any smoothing. So that searches for the maximum in this trace and yields the photon energy of our pre-edge peak, and it yields the height on the y-axis here of this pre-edge feature. So this is the easiest approach to analyze this region and to determine position and height of this pre-edge peak in the XANES spectrum of vanadium pentoxide. The next possible approach is refining two profile functions to this region in the XANES spectrum. Profile functions are selected by the menu item least squares fit, and we see a number of profile functions now that can be used for XANES analysis. Profile functions and step functions are available here. We want to select two profile functions now, one for the pre-edge peak itself and one for the rise of the absorption edge, and we want to go for a pseudo-Voigt function, which is a mixture of Gaussian and Lorentzian function. Click on OK, and next we have to select suitable starting parameters for the refinement: height, position, and the full width at half maximum. In this input box, the parameters can be selected by clicking inside this box. Basically, for a height, you click twice at top and bottom. For the height, the position is just one click. If you want to change the parameter that you are working on, you can just use the right mouse and switch between those. So now we are positioned again, switch this back to where it belongs. And the width again is a distance. So click here and there for the width of this peak. Need to do the same for the second peak. Here, select a height, a position, and a suitable width. So those are the starting parameters for the refinement. They should be close enough to start the refinement now. And this is the result. The red trace is the experimental XANES spectrum. The blue trace is the sum of the two profile functions that we have selected, and the dashed lines are the individual profile functions. You see the agreement between experimental data and the profile refinement is not that great, mostly because we are trying to refine an asymmetric profile with a symmetric profile function, and this is accounting for the differences we see here. So we want to try this again, and instead of selecting a symmetric profile function for the pre-edge peak, we want to try an asymmetric profile function. So we repeat the procedure, least squares fit, and instead of two pseudo-fold function symmetric profile functions, we select an asymmetric forked function. And again, we have to input the parameters. Note now that those are the starting values for the symmetric forked function. There's a certain order in the program how those profile functions appear in the refinement and also in this a selection of starting parameters. And so this is actually what we want to use for the edge. So we have to shift this peak over to the edge and use the next peak now actually for the pre-edge peak. So since now we have an asymmetric profile functions, we need to select two full width at half maximum, left and right. One is selected, but the other one we need to input here. And those are now the starting parameters for this refinement of an asymmetric profile function to the pre-edge peak and a symmetric profile function for the absorption edge. So those are the results, and now we see a better agreement between the red trace and the blue trace, between the experimental spectrum and the sum of those two profile functions. Can click on OK. And now we have from this refinement a number of parameters, for instance, position of this pre-edge peak, the height, the width, and also the area under this pre-edge peak if we wanted to use any of those parameters for calibration, for instance, for determining average valences of unknown materials based on those references. The next procedure is performing the same refinement, but not to the original spectrum, but to the first or second derivative of this spectrum. This procedure may be beneficial if you have strongly overlapping features in the XANES region that you can hopefully better resolve by performing the refinement to the first or second derivative. If you want to do this, it's recommended to perform the refinement first to the original spectrum and then use those values, those parameters as starting parameters for the refinement to the first or second derivative of the experimental spectrum. So this is what we're going to do now. we need to calculate the first derivative of this spectrum. And again, this is in numerical procedures. We see differentiation, and we want to use splines for this calculation of the first derivative. We do not want any smoothing or any leveling out. We basically want just the interpolation, and for that we are even going to increase this parameter. Again, those procedures are being explained in the manual in greater detail if you're interested. So, okay, and this calculates now the first derivative of this section of our XANES spectrum that includes the pre-edge, peak, and the rise in the absorption edge. So now we can go back to least squares fit. We use the same profile functions that we have already selected, but now we need to select refine of the following derivatives, and we want to use the first derivative because this is what we just calculated. Okay, and now we can use the parameters that we have determined in the previous refinement as starting parameters for the symmetric profile function, for the asymmetric profile function, and click on OK. And then we perform the refinement to the first derivative of the experimental spectrum. The blue trace now is the first derivative, the calculated first derivative of the sum of the two profile functions that we used for the refinement. So, what's next? Well, now that we know how all this works, we can, of course, apply a similar refinement of a sum of profile function, not only to a section of the XANES, that includes the pre-edge peak, but to the entire XANES spectrum. And this is what we are going to do. So again, we select a section of the spectrum that includes a good portion of the pre-edge region and the XANES. And we're going to refine a sum of profile functions now to this spectrum, including the step function for the edge, the pre-edge peak, and those features as well. We already know we need an asymmetric profile function for the pre-edge peak, but we're going to use symmetrical profile functions for the other features here in the XANES. So let's get started. Least squares fit. We need one asymmetric profile function for the pre-edge peak. We need a step function here, and we need a number of symmetric profile functions that we can use in the refinement. There is certainly one additional feature here in the edge, and then let's say we want to use 1, 2, 3, 4, 5, at least 5 additional symmetric profile functions for the refinement. Click on OK, and now again we have to select the starting parameters. So this is for the first symmetric profile function now in the edge. That's fine, we can take this. This now we need to shift, because this corresponds to this peak here with a reduced height. Next feature is height, the position, and the width. Again, we have the height, the position, and the width. This feature, we have height, position, and width. We have the asymmetric profile function now that we want to use for the pre-edge peak, height, position, left and right, full width at half maximum. And we have the step function now. So this is the height, the absorption edge, position, and width. So those are the starting parameters of this refinement, and they should be close enough now so that we can start with the refinement and see what we get. So this is now the result of this refinement, blue and red trace. So a sum of profile functions basically refined to the entire XANES spectrum. So this can be performed to the original spectrum, and of course this can also be performed to the first derivative. So we are going to try this as well. So again, calculate the first derivative here of this spectrum and start the refinement again. Least squares fit. We are going to use the same number of profile functions here, a step function, but we're going to refine the sum of all those functions to the first derivative. And again, we can just use those parameters, all the parameters that we already have as starting parameters for the refinement. Click on OK. And so then this is the result of the refinement of the sum of all those profile functions to the first derivative of the XANES spectrum in the chosen range. So now that you know what is possible, it begs the question, what is recommended? In general, I would recommend a simple and stable procedure to determine the edge position and to use that value then in a calibration curve, for instance, to determine the average valence of unknown material over a total refinement to the entire XANES region as it is shown here. Apparently, so far we have not talked about number of independent parameters, confidence limits, and statistical significance of the parameters used in this refinement. This is a rabbit hole I do not want to go down now, but we will have to talk about this when we are looking at the XAFS refinement, and all the things that we are going to say there, of course, also applies to profile fitting in the XANES region. So a simple but stable procedure is recommended. What can a simple yet stable procedure look like? So that's a bonus tip at the end. A very stable yet simple refinement procedure uses just the step function, for instance. So if we look at the entire spectrum of vanadium pentoxide as shown here, we select no profile function, but just the step function for the refinement. Adjust the height, the position, and refine this step function to the XANES spectrum of vanadium pentoxide. So this is very stable and it yields an overall inflection point. So the position now of this step function can be taken as the edge position. So this procedure now can be applied to other reference oxides, for instance, and we do have those available in the data folder. So for instance, let's look at V203. Open this. We perform the same refinement. So just a step function, height, position, and width, and refine this step function to the experimental XANES spectrum of the vanadium 3 oxide, and we have one more of the vanadium 4 oxide. We can use this as well. Same procedure, just a step function, height, position, and width, and refine that to the experimental spectrum. So now we have those three spectra, three reference oxides with their respective refinement of this step function. And those position of the step function now for those respective oxides can be used to assemble a calibration curve. And the benefit of using this step function is that it's a very stable procedure that is less dependent on the overall shape of the XANES region. So for instance, if you are looking at in situ experiments, monitoring chemical changes in your material that are accompanied by significant structural changes and hence changes in the XANES, it may be difficult to select particular features for a stable determination of the edge position. And then this simple step function refinement will at least give you a decent idea of the evolution of the average valence of your material under reaction conditions. So now if we look at what a corresponding calibration curve actually is, then I have that prepared, and this is what you would get if you plotted the average valence of the reference oxides as a function of edge position. So linear regression, and we see we get a very decent calibration curve here from those simple step function refinement to the three references that we have available here for the vanadium oxides with valences in the range from 3 to 5, and we can use this calibration curve now to determine the evolution of the average valence, for instance, of vanadium samples under reaction conditions. So, but this is something I want to show, but in another tutorial, of course, when we are looking at a batch analysis of theories of spectra collected under reaction conditions from in situ experiments. So that's for later. This is it for now for this tutorial, and I sure hope to see you in the next one.